Ready? Okay, we have spoken about the problem of finding the right mathematical model for describing some phenomena. Okay, now the problem is, how do we invent the equations for describing some phenomena? So, for instance, I want to describe the motion of planets. I want to describe the flow of a fluid inside a pipe. I want to describe the economical behavior of nations. I want to describe the evolution of DNA of a species. I have a set of phenomena, and I want to describe mathematically, I want to invent a mathematical model for describing, forecasting, controlling what happens. Okay. Now, what we must talk about is a kind of meta-theory. So let us try, this is a Greek word. Theory is a Greek word which means a sequence of hypotheses made for describing a certain phenomenon. This is the meaning of this Greek word. Then, meta means beyond. Meta-theory is a theory which is teaching us how to build theory. So, for instance, the equation of the motion of a material particle are describing the behavior of physical objects which are moving in space. So the theory of material particle allows us to describe the motion of objects in space. What we will talk, the subject of the lecture today is a theory which is teaching us how to build theories. Okay? So it gives us the basic ideas for learning how to build theories. For this reason, in posterior analytics by Aristotle, there is the new word meta-theory. Okay? The Aristotle posterior analytics is a book in which we have learned how to build mathematical theories for describing physical phenomena. So I'm not talking about something new. It is 3rd century before Christ. 2,300 years ago. It is an old theory, which has been forgotten because we risk to enter a new Middle Age. But this is another story. We'll talk about this another time because today I want to be rather technical. Fabio will teach you more details about the principle of virtual work in some of the next lectures. Here I want to follow the presentation of an Italian historian of science, Vailati. He wrote a very nice paper at the end of 19th century in which he describes the origins of the principle of virtual work and its application as a general principle for building new theories. Okay? And I will use a very, very simple example. I want to tell you now, I open a small bracket, parenthesis, because I want to tell you that Vailati attributes the principle of virtual work to Aristotle, because there is a book by Aristotle which is called Mechanica Problemata. In Greek it means mechanical problems. Everybody here studied physics first year. Okay, so everybody among you studied simple exercises, equilibrium of a lever, the resultant force applied to a body for being in equilibrium has to be zero, the balance of torques or moment of forces. This Mechanica Problemata is a list of problems which are solved without theory. What happened? In Middle Age, people became, like now, practical. So they did not want to study heavy theoretical books they claimed were useless, and they wanted immediate solutions to practical everyday problems. This is the first thing. Second thing, for some reasons which we could discuss, in Europe during Middle Age we had a strong influence of Roman Catholic Church on science and culture. So Epicurus was considered a bad philosopher, while Aristotle was considered a good philosopher. Okay? So, an unknown monk who was copying the ancient books, because printing is rather modern. Those times books needed to be copied by hand. Do you know the value of a manuscript in 13th century? One manuscript, like a book you are using now at the university, had a value equivalent to a farm. They were very expensive. So there was a strong selection in what had to be copied and what was not copied anymore. Okay? An unknown monk decided that in order to save Mechanica Problemata, he had to change the name of the author. So he pretended that the author was Aristotle. This is the theory of Winters from Nebraska University, who wrote a very careful paper about Mechanica Problemata. So what I will tell you is the union of what I have read in Vailati and what I have read in Winters. Okay? at the end of the story, most likely, this is the theory of Winters, the principle of virtual work has been proposed by Archytas of Tarentum. Tarentum is a city in South Italy which has a very complicated history. Just for joking, I will tell you that Tarentum has been Greek, Roman, Islamic. There was an emir of Tarentum. Why? Because Venice, in order to cause troubles to the kingdom of Napoli, helped Turkish to conquer Tarentum. You know, dirty politics is not an invention of our politicians. Okay? Venetians were helping Turks to conquer an Italian city. Archytas of Tarentum invented, probably, the principle of virtual work, and he applied it to find the equilibrium of a lever. So, unfortunately, Vailadi is written in Italian and has not been translated yet. But Winters, if you digit in the web Winters and Archytas of Tarentum, you find in the web the paper he wrote about this subject. Now, why this is so important? I try to explain you. I have chosen a simple problem, a simple physical problem, to show you how we can invent a model, a theory, for describing the behavior of this simple physical system. Okay? Now, somebody among you, I don't know why I don't see here the master students, but okay. There are? Okay, there are. Some physical problems, now, you want to study which are new. You want to study martensitic phase transformation, and nobody knows how to invent the equations for describing this system. Now, the question is, what has been done by Archytas of Tarentum for solving the problem of the equilibrium of a lever? We learn what Archytas did, and being inspired by his method, we try to invent new equations. What can we do? This is our idea of science. Right? So, even if studying the equilibrium of a lever is simple, somebody can tell me, I already know how to do it. Let us read the sources and let us try to understand how, for the first time, people invented the solution of this problem. Because in this way, we can try to repeat the process. The idea is very simple. Okay, so the drawings of ancient Greek texts are lost. Because, you know, even at the epoch of Middle Age monks copying the books, pictures were expensive, not only now. So we have found the descriptions with words, but we don't know, we don't have the pictures. So we use the modern symbol. So you have a rigid bar, here you have a pivot, this is long L1, and this is long L2. Okay, then I apply F1 here, and I apply F2 here. So I assume that here I have a weight, which I call F1, and I have applied here F2, which is another weight. And I ask myself when this system is in equilibrium. Okay, now I know that you have studied this problem in another way. But let us go now to see how this problem has been solved for the first time. Because we must learn, if you want to become a scientist, you must learn how people solved the problem without knowing the solution. How they invented a new solution. Okay? Okay. So the idea is now very simple. You, first of all, must describe the kinematics of your system. So the first step is kinematics. French nowadays is not used anymore, but D'Alembert, I hope you heard the name D'Alembert, and you know that French Revolution was writing the revolutionary encyclopedia by Diderot and D'Alembert. D'Alembert wrote that in order to describe a physical system, la cinématique d'abord. You must start with kinematics. So the very preliminary move is how to describe the kinematical behavior of your system. We already have spoken about this, right? Okay, how many degrees of freedom do you have for a lever? 1. The possibility of motion of this lever is the angle of rotation around the pivot which you have placed. So you have a one-to-one correspondence between the angle theta and the state of the lever. Now, we have a list of assumptions. Do you remember we said that every theory is based on a series of conjectures. We assume that this is a rigid bar. It is not deformed because of the externally applied loads. We assume that there is no constraint which is blocking this rotation. Okay? So we have a list of assumptions.
We're not considering the translation.
We are assuming that this point cannot move. We have blocked it. In engineering, when you draw this, it means that only rotations are allowed. This is an ideogram, which means no translation allowed. Okay? Okay. So the state of the system, you remember, we distinguish between the state and the configuration. The state of the system is mathematically modeled by the angle theta, and the space of configuration is a circle. Because when you know the angle theta, you know the configuration of your system. So you have a one-to-one correspondence between the points on a circle and the configuration of your lever. Okay? Okay. So, among all possible configurations, we want that the configuration theta equal 0 is an equilibrium configuration, and we want to find the value of f1 and f2 such that theta equals 0 is an equilibrium configuration. So we want to invent a mathematical theory which is forecasting for which value of f1 and f2 this system remains in equilibrium with theta equals 0. Now, for us, this is a simple problem, but imagine 2,300 years ago, this was the boundary of knowledge. Okay, they needed to invent a basic principle, and this basic principle had to be applied to this problem for forecasting the condition for f1 and f2 giving equilibrium. Okay? Unfortunately, we don't have the book of theory. So we do not know how Archytas was explaining the mental process which led him to solve this problem in a certain way. Why? I am repeating this. I hope that also in your country middle age is considered a very negative period. I hope so. Okay, in Europe we consider middle age a very negative period. It is a period where no democracy, no science, no freedom, slavery, few people controlling everything. This was a very bad period with some good aspects, but middle age was considered a very bad period. A period where science was kept in the hands of few monks who were waiting for the light. Enlightenment is the period, 18th century, the period of French Revolution, where the lights of reason started to burn again. Okay, so why I'm telling you that middle age is a bad period? They believed that the book of theory was useless. And they did not copy it anymore. They wanted only a list of solved problems. So what I'm telling you now is the reconstruction via the solution which we have in Mechanica Problemata, the reconstruction which is due to Vailati and Winters of the ancient reasoning of Archytas. Okay? Now, we postulate that equilibrium is attained in one configuration, starting from which the work of all applied forces for every small displacement starting from the tentative equilibrium configuration is equal to 0. So the principle of virtual work is the following. Equilibrium is possible only if the work of every applied external action for every virtual displacement. Why virtual? Because it is imaginary. I imagine to move a little bit the equilibrium configuration, and the applied forces must do some negative zero work for all this virtual displacement. Okay? This is what you can imagine was the leading principle in the head of Archytas. This is a statement of very general applicability. When you have a generic physical system, a fluid, a solid, a deformable body, a rigid body, an economical system, a biological system, everything, phase transition. The principle of virtual work tells you, describe the kinematics, find the expression for virtual work for every virtual displacement, to find the equilibrium, impose that the virtual work is equal to zero. This is a general recipe which applies for describing every known physical system. Okay, now I use the word physics in the Greek sense. Physike in Greek means what is natural. So for me, physics means everything which we are observing in reality. Okay? So I want to apply the principle of virtual work also for describing the biological phenomenon leading to the equilibrium between a predator and a prey. I don't want to apply it only to the equilibrium of a mechanical system. Okay? So it is a very general idea. Now let us see how we can proceed. Estimating quantitatively the condition for equilibrium. Okay? Now, if you have here, of course, the virtual displacement can be very small. Okay? So even if I have drawn a big theta, I will confuse the arc of the circumference with the straight line, which is the chord of it. Okay, this is true when theta is very small. Okay, usually in the principle of virtual work we call delta theta, because delta in the Greek tradition is something very small. Okay? Okay. So, this is L2. This is L2 delta theta, and we confuse, we say that this is very close to this segment when delta theta is very small. Okay? Now, if you have here applied the force F2, the work of F2 in this displacement is F2 L2 delta theta. If delta theta is positive, so we assume that this is the positive direction of positive variation of angles. If this delta 2 is positive, then this work is negative, because F2 is pulling down, delta theta is positive, so this displacement is in the opposite direction with respect to the direction of F2. So we must place minus here. Okay? Then let us consider what happens here. Everything is like as it was before. So the displacement, the virtual displacement of the application point of the force is equal to L1 delta theta. The applied force is F1. However, for delta theta positive, this is a positive work because it is in the same direction of F1. Okay? So this is the evaluation of the virtual work for a virtual displacement for the considered system. The principle of virtual work tells us that this has to be equal to 0 for every delta theta. So, the equilibrium of a lever is attained when for every virtual displacement, admissible virtual displacement. Let us slowly consider this. Your bar is rigid, so this point can move only along this circumference. You cannot elongate the bar. You cannot, this pivot is blocking this point, so this point cannot move back and forth. So you are considering only the admissible virtual displacements. The displacements which are allowed by the applied constraints. Okay? For every admissible virtual displacement, the total work, virtual work, has to be 0 for every virtual displacement. Now, for Greeks, algebra was a difficult business. They needed to make geometric reasonings for proceeding. We own now algebra. Okay? In Europe, we say that algebra is an invention of Arab scientists. For sure, after Middle Age, algebra came to Europe via the translations from Arab into Latin, translation made in Spain. Salamanca University, or all the universities in Spanish, Arab Spain. Okay? So you are not afraid to say that this is equal to 0 if and only if you can place delta theta, you can extract delta theta, and you have this number. So you have one number multiplied every delta theta, it has to be 0. Which number multiplied for every delta theta is 0? I mean, every number multiplied 0 gives you 0. So there is no number that multiplied 0 gives you 1. Okay, if you want I can give you a lecture about basic algebra. Okay. By the way, in the cuneiform tablet of Mesopotamia, of mathematical content, you find this demonstration. So this is again a very old theory. Okay, so you want something that multiplied for everything gives you 0. This something can be only 0. So, using the principle of virtual work, you prove that equilibrium is given by this equality. Or, if you prefer, F1 times L1 equal F2 times L2. Okay? This is the condition for equilibrium. The first time when the equilibrium of a level has been studied, and the first time when we have the solution of this problem, so when this problem was at the boundary of knowledge, they used the principle of virtual work. Nowadays, they are teaching you the balance of moment of forces. I think that if you are patient, we will teach you how balance of force and balance of moment of force is a consequence of the principle of virtual work. The bad news is that the vice versa is not true. It is not true that for every mechanical or physical system, balance of force and balance of moment of forces implies the principle of virtual work. So, the principle of virtual work is more general. It is valid in some cases in which balance of force and moment of force is not enough. The principle of virtual work applies to describing every equilibrium configuration. There are some equilibrium configurations which cannot be found using only the balance of force and the balance of moment of force. Okay? So you must be very careful in understanding this idea. Okay, so let's move some step further. I mean, this is a very simple example. However, this is the prototype, the general scheme which has to be used for describing equilibrium. Okay? Now, let us talk about another principle. Equilibrium. Let us say stable equilibrium is in the configuration which minimizes total energy. This is another meta principle. This is another basic principle. So, let us try to organize ideas. Archidas was telling the following recipe. Do you want to find equilibrium? Write the virtual work for every admissible displacement. You will see that this idea works for continua, works for discrete systems, works for fluids, works for solids, okay? Impose that every virtual displacement has the total work, the work applied by every applied action equal to 0, and then you get equilibrium. Okay? Now I give you another principle. This principle is find total energy, look for minima, you will get stable equilibrium. Because there are different kinds of equilibria. I will tell you how to distinguish these different equilibria. So you can tell me how many principles you are telling. Which one is the one I should use? Okay. Let us discuss a little bit this principle of minimum of energy. Then we discover that if the principle of minimum of energy is accepted, then the principle of virtual work holds. Therefore, the principle of virtual work is more encompassing than the principle of minimum of energy. So actually, we must use, in general, the principle of virtual work. However, the principle of minimum of energy, when applicable, is very useful. The typical example is this one. Imagine to have a metallic wire having this shape, and imagine to have a small plastic particle with a hole, and imagine to have perfect, without contact between the particle and this metallic wire, so there is no friction. So you can ask yourself, where can I place my particle with zero velocity, and this particle remains in the position where I place it? You discover that, of course, we are imagining that you have gravity, and this is a metallic wire which is vertical. Okay. Then I think, I hope that you know that if I place in a minimum or in a maximum of gravitational energy, the particle remains there. However, if you give a small velocity from one side or the other side, this particle falls and goes away. Maybe it goes back and then it's doing different motions. So there are some equilibria which are unstable. And there are some equilibria which are stable, because if you give a small velocity to this particle here, it remains around the equilibrium configuration. Dirichlet, the famous French mathematician, characterized minimum of total energy as the set of stable configurations. You needed to wait until Lyapunov, a famous Russian mathematician of 20th century, before having a complete theory of stability of equilibrium. However, what is clear is that if you have a total energy, your system is in equilibrium in maxima or minima, okay? And stable equilibrium is attained when you have minima. So if you are an engineer and you are designing a system which must behave in a reasonable way, this building, for instance, you want that its equilibrium configuration is a minimum of energy, because you don't want that a small perturbation of this system will drive the system very far. Okay? So, the principle of minimum of energy is very useful for finding the equilibrium, the stable equilibrium. Okay, now this is a system with 1 degree of freedom. If instead of having a system with 1 degree of freedom, you have a system with n degrees of freedom, we will discuss this with Luca and with Fabio. Imagine that you have n parameters characterizing the configuration of your system. Following the tradition established by Lagrange, we call it Q1, Q2, Qn. Okay? The total energy of the system, U, is a function of Q1, Q2, Qn. Which is the equilibrium, the stable equilibrium configuration? The stable equilibrium configuration is where this U has a minimum. The unstable is when this system has a maximum. I hope that you have studied something about mathematical analysis. In particular, I hope, but I will tell you the ideas, that you know how to find minimum or maximum of a given function of n variables. Okay? Which is the basic idea? Okay, instead of calling Q1, Q2, Qn, I call it Q. It means one vector having n components. The candidate equilibrium configuration, I call it Q star. So I want to find Q star such that for every Q close to Q star, this equality is verified. So I want to find, I have Q star, I vary Q star a little bit, and I go to Q, very close. And I want that the value of U is greater or equal to Q star. Okay. I can say that Q is equal Q star plus delta Q, and delta Q is small. Okay? So I want to characterize the set of Q stars such that varying a little bit Q star, total energy increases. I don't know, because we don't have any Greek text, how this problem has been studied in Greek mathematics. I can tell you the following. Recently, it has been discovered, I will tell you how in one of the next lectures, it has been rediscovered, an ancient book by Archimedes. This book is called On Floating Bodies. This is the theory of how we can build a shell which is floating and which is stable with a small variation of angle. No, this is a very technological problem. You have this shape of the profile of a boat, and what you want, the water is here, and if the angle with the vertical is theta, you want to find this shape in such a way that it is a minimum vertical direction, is a minimum of energy with the biggest possible angle. This is very important for the technology of building boats. Okay? Archimedes designed the shape of the floating part of boats for having a very wide angle of equilibrium, stability of equilibrium. There is a text which is available, it is in Greek, translated into English. The book is called On Floating Bodies. So the concept of stability of equilibrium was already known to Archimedes. For sure, he knew how to handle the problem of minimum for total energy. However, we do not have the textbook. We have only the solution of a problem. Okay? Now, in modern times, we are using, this is another crucial concept, Taylor expansion. Okay? I do not know the value of UQ, but I can approximate it. I say that UQ is equal to UQ star plus gradient of U calculated in Q star dot Q minus Q star plus infinitesimals of higher order. If you don't remember this, I write it explicitly. By the way, somebody has shown me this morning a very lengthy expression component-wise. Think, this is a compact form for writing the same equation in a short way. Now you can write in this way, U Q1, Q2, Qn equal U Q1 star, Q2 star, Qn star plus du over dq1 calculated in Q star times Q1 minus Q1 star plus du over dq2 Q star Q2 minus Q2 star plus du over dqn calculated in Q star Qn minus Qn star plus, you see, it is already bigger. The two expressions are totally equivalent. However, this is shorter, so if you know the meaning of this, you can handle it in a better way. So I don't claim that the equations you have written are wrong. They are too big. And one must find a symbolic way for writing them in a shorter way. Then you will write a code with MATLAB, with Mathematica, with Console, which makes all the calculations. Okay? If you have a shorter equation, your mistakes are less likely than if you have a bigger equation. This is the genius of Levi-Civita. The compact notation has been invented by Tullio Levi-Civita, who invented the way for handling these equations in a more compact way. Okay, now let's go back to Taylor expansion. When Q is close to Q star, these quantities there can be neglected. So you can write for very small delta Q, for very small delta Q, you can write UQ equal UQ star minus UQ star equal grad U dot delta Q. Okay? If Q minus Q star, you call delta Q. Now, this is bigger than that. So this has to be greater or equal to 0. Here a mathematician will be very upset. I am being very brutal. Okay? Because here you have plus something. But I remember that, I hope that you remember a theorem which is called the theorem of permanence of sign under the operation of limit. Okay? So in order to have that this equality is true, this is negligible. When delta Q is small, then this inequality has to be true for this approximation. This is brutal, can be done in a very rigorous way, but you agree with me, Taylor expansion tells you that the increment can be very well approximated by the first term of Taylor expansion. So if very well approximated, it means that this is equal to that, and this has to be greater or equal to 0. Okay? We have a problem. This has to be, what I'm telling you drives me to suspect that Architas of Tarentum was minimizing something. Why? Because this has to be greater or equal to 0 for every delta Q. Something is a minimum if for every variation of the independent variables this value is always positive. So I have no proof because I have no books. I have no ancient books telling me how Archytas was developing his principle of virtual work. But if you ask yourself, why for every virtual displacement something has to be equal to 0? How you think this principle? You think this principle. Why? Because you have a function. You want to find the minimum. Local minimum. So you have a Q star, you vary a little bit Q star, you get Q star plus delta Q. You truncate your Taylor expansion, and you get that this animal has to be greater or equal to 0 for every delta Q. Okay? Now, if you look at this expression down here, this is a linear function of delta Q. So, if this is positive for a certain delta Q bar, then it is negative for minus delta Q bar. What this means? It cannot be positive. It has to be 0. If ab absurdo it were positive for a certain delta Q bar, then with minus delta Q bar it could become negative. It cannot be negative, because it is a minimum. Therefore, for every delta Q, this equality holds. What we have proven, minimum of energy implies that the total work for every virtual displacement is equal to 0, where grad U are forces applied to your system. If you call grad U the force applied to your system. So if you have a total energy and you call grad U the applied forces, then the principle of virtual work is a consequence of minimum of energy. If you don't have a total energy, you directly postulate that the total work of all applied actions has to be 0 for every virtual displacement. So, I don't know if Archytas was following this reasoning. I know that D'Alembert was using this reasoning. And I find it very likely that the reason for which the principle of virtual work has been postulated in the way we are learning, the reason for which this postulation has been done in this way comes from the condition of minimum of total energy. Okay? So if we call conservative those systems for which you have a total energy, the principle of virtual work is completely equivalent to the minimum of energy. If your system is not conservative, you don't have a total energy, you can still keep postulating the principle of virtual work. Do you want to study the equilibrium of a fluid? You have a particular form of the principle of virtual work, you apply it and you get equilibrium of fluids. Do you have a complex machine? You apply the principle of virtual work, you get equilibrium. You have a deformable body, you change a little bit the form. You change the actions which are applied to your system. And you get from the principle of virtual work the equilibrium. I conclude this telling you that general relativity, they believed in general relativity only when Hilbert and Poincaré found a variational principle for general relativity. Quantum mechanics has been invented postulating the principle of virtual work. To my knowledge, every new theory has been formulated the first time with the principle of virtual work. Of course, I cannot prove it. I don't have the access to every idea and every written text which has been written, or every idea which has been taught during history of science. Okay? In a sense, this is a personal belief. But what I can tell you is that I never have seen a good idea which has not been developed using the principle of virtual work. Okay? So now what you will do? Slowly, because we need time, slowly you will see how, using the principle of virtual work, you can build fluid mechanics. You go, you read my paper with Nicolas Frey and others, and you will see how slowly, postulating the minimum of energy, you get the equilibrium conditions. Solid mechanics, it has been developed in this way. Mechanics of machine, electromagnetism, everything has been developed using this criteria. So, what we have said. Let us make the resume of my lectures up to now. We want to forecast the behavior of physical systems. Mathematics gives you a model for forecasting the behavior of these systems. You start with kinematics. You want to discover equilibrium or motion. In order to find equilibrium, look for the minimum of energy or for the principle of virtual work, so the configurations which makes zero the total applied work. In one of the next lectures, you will follow the ideas of Lagrange and we will try to see how the motion can be seen as minimum of something. This something is called action. Okay?
If you understand this, you can invent everything. There will be no theory you are not able to invent. Okay? So trust, not me, trust Lagrange. Okay, this is the idea of Lagrange.